Good afternoon, everyone, and thank you for joining us today. This is part of our Microgrid webinar series with Brian Patterson, who's the chairman and co-founder of Emerge Alliance. Brian works on all things microgrid over at Emerge Alliance, along with AC and DC power. Today, we'll be talking about the anatomy of a microgrid and the pros and cons of AC and DC coupling. A few things to note before we get started today. You can visit all of our future webinars at events.solar, and that's a good way you can sign up for each webinar in there. It has all sorts of dates listed out. There's also a webinar tonight, which Brian can talk about more once we get into this, more of a after hours event with everyone in a relaxed atmosphere. So this webinar is sponsored by Emera and Block Energy, Primer, NorCal Controls, and Power Engineers. Without their help and sponsorship with this, it wouldn't be possible to bring in Brian and Lewis. So without further ado, I will hand it over to you, Brian.
Oh, thank you very much, Greg. And we're going to jump right into it because time is somewhat limited. And a little bit of a town hall style here where we're going to hopefully have some time for questions, although many of you sent in questions, and Lewis and I will try to answer as many of those in the context of the dialogue as we go along. Obviously, we're in an unusual situation with the outbreak of virus and so on. But it's yet again another kind of canary in the coal mine reminder of how vulnerable some of our national infrastructure is. And, you know, we've been warned many times regarding the power grid and how vulnerable it has become over time because it's under pressure. Some of it very old, although it's been tried to be modernized along the way. But you can just imagine what it would be like today if we were to have a major power failure on top of being sheltered in place and so on. We'd be sitting perhaps in the dark and maybe even without communications. The encouraging part of this is that there's a lot going on with microgrids, and many of us are seeing, and I hope you maybe are sharing the feeling that there is some electric light, if you will, at the end of the tunnel for microgrids. And a lot of our lawmakers are starting to dig in various parts of the country, and maybe you know, the epidemic that we're in right now will be an inspiration for some people to take a harder look at what's going on. We have a guest today, a really significant contributor to some of the new thinking that's going on in microgrids and microgrid networks, and that's Louis Zebieta, who is with Block Energy, Emera Technologies group. Emera actually is a regulated utility, but the Emera Technologies is unregulated, and Block Energy is their platform for utility scale type microgrids all the way down to home scale microgrids. And I'm sure Louis will sneak in a few words about that as we go along. Louis was formerly of Arta Power, and for those of you who also know Arta, they are big proponents of microgrids and fielding a lot of stuff there. So let's jump right into the anatomy question of microgrids, and I'll ask Louis to comment as we go along. But I want to start out and just say simply, you know, you go through all the definitions of a microgrid, but since we're just talking about anatomy here, there are kind of four major components that make up a microgrid. The supply of electricity, the storage of it, the loads that it services, and then to integrate those three, you have some connectivity and management that becomes a part of it. For each of those categories is sort of subcategories, and we'll go through a little bit of it. But in storage, you can have chemical storage, you know, the kind of traditional battery types and so on, and then mechanical, some, you know, pump storage and other types of mechanical flywheel and so on. Supply, same kind of thing. You have traditional non-renewables, largely fossil fuel, you know, ICE, combustion generation. And then you have renewable, the newer renewable stuff. On the load side, that's where a lot of change is taking place. It used to be, you know, toasters and things like that, but now a lot more of it is electronic. So we're moving into more inductive and digital type electronic loads. And then in the middle, there's this question which we're going to try to poke around today about DC coupling and AC couple. You know, how do you bring all this stuff together in a rational way? So Louis, you've been dealing into microgrids for some time now, and I guess initially most people thought of you know, the new things in power as just solar on your rooftop or on a building rooftop, but it's expanded quite a bit, hasn't it, over the years? You're with me, Louis? You may be on mute.
Brian, thank you very much for inviting me. It's a pleasure being here, and I'm glad to see so many people thinking on microgrids. Yes, you're right. One of the main reasons we started looking into microgrids was the change that we saw in the energy sources. Before, energy was coming from the large central plants and moving to the load, and we started seeing wind and solar as distributed sources, and then we start thinking, okay, how we bring these energy sources into the grid, and that is where microgrids are, right? Because it's an easier way to integrate these resources. Now, when we think about microgrids, we have to think not only about the sources that we have at the moment, the sources that are coming in the future, fuel cells, for example, and maybe CHP, how we're going to integrate all these new sources that they are doing research on when they become available, and the microgrids should be flexible enough to do that.
So I guess, Louis, and I don't know if I'm the only one, but your microphone is breaking up a little bit. So, but in any case, I guess what you're really saying is that the number of sources now has expanded quite a bit and will continue to expand over time. Whereas things started out as solar and then solar storage combinations. Now, multiple sources are starting to combine. And of course, each of those sources has subcategories. Again, solar, you know, big solar, small solar, the CHP stuff is quite a diverse universe, as is even fuel cells. You know, some of them using hydrocarbon type fuel supply, some of it hydrogen, and so on. So there's a lot of diversity there. So one of the tricks, I guess, about a microgrid is it's got to be prepared for new technologies coming along. How about storage? Is storage something that is critical to a microgrid, and if so, why?
Brian, if you give me a minute, I will try to call from my telephone line to see if it's better.
Yeah, are you on your telephone line or are you on a microphone now?
I am on the phone line.
Yeah, it's still breaking up for some reason. But in any case, go ahead and I'll try to fill in. Okay, I think we lost Louis. All right. But in any case, the storage is kind of in the same boat where right now there's a strong emphasis on lithium-ion battery technology and, of course, repurposing of lead-acid batteries and things like that. But there's a lot of new thought process going into storage, and some in the larger storage, of course, the pumped hydro and things like compressed gas and so on. But I don't think for any moment that we won't see new sources of energy being stored in new and unique ways. And so again, you have this kind of split between the chemical storage, which we would kind of overlay and call batteries and capacitors and things like that, and then mechanical stuff where you're taking the energy and storing it in a mechanical way. In any case, areas loads, and as we said before, and Louis, jump in anytime, and if your microphone gets better, I'll let you go ahead. Otherwise, I'll try to fill in for you here. In the load category, you know, we're used to the appliances and plug loads in buildings and things like that. Now, a lot of that is being controlled, either remotely or sensed or by computers and timers and things like that. But we're also adding some rather significant loads, some real game changers, vehicle storage, the vehicle onboard batteries, and then also shared storage in a system. And of course, you can view any of this loads as other microgrids. If you're going to export power, you can look at all of that as loads, whether it's peer-to-peer exporting or up to another tier or even directly to the grid. So there's a lot of new consideration and loads that have to be managed, again, in the microgrid. The thing about loads, I guess, that everybody focuses on is how the loads then can be articulated or modulated. And that's part of the role that a microgrid can play. You can either have subsystems that modulate a lot of the load utilization, or you can actually have the microgrid itself start to play a role in managing loads, particularly in terms of signaling times where power is in the critical demand, or whether things can be scheduled, et cetera, et cetera. Also, in a transactional way, the loads that are community and regional get played against what the local needs are. And so the microgrid can play, particularly in what you would call an advanced microgrid, would play a role in the transactional analysis of whether you should be importing power or exporting it to the bulk grid or to a neighbor. In any case, that management now takes on a whole new set of equipment, if you will, that becomes that management and the connectivity between all these elements. Starting off with basic controllers, inverters, rectifiers, transformers, a lot of the traditional things that you bring together, but a lot of new things as well in terms of the way things are switched and the way they are safety, what you're doing for power protection and things like that, and metering and monitoring, because that's a big element in terms of determining how the microgrid is going to transact the power. And the list kind of goes on and on. The way distribution is done, we're seeing some new types of cabling and new ways of configuring the physical connectivity of a microgrid together. What I haven't mentioned, of course, is all of the human side of it that's involved in engineering and design and deployment and construction and so on, and then the final operating and monitoring of microgrids. So all of those, you can think of the service element or the management element of the hardware as a whole set of another element, if you will, in the whole system. And here's where we get into that question of how do these things get connected together in electrical terms. And the two basic categories we're going to talk about today are AC coupling, where things are synchronized to an AC bus of sorts, or DC coupling, where you go non-synchronous. And then perhaps if you're feeding AC loads, you invert to get to the load, or you might invert to get back onto the grid. In any case, the other considerations before we get into the coupling directly is scaling. A lot of people originally thought microgrids were something that utilities worried about. Other people thought, no, that's what's going to be in my garage and on top of my roof. But actually, it's everything in between. There's utility scale microgrids, some of which will service, substation at the substation level, all the way down, to the local neighborhood. But there's also microgrids that are in the building and maybe even parts of a building. We've seen microgrids be deployed at a floor level in a multi-story building, or at a tenant level in a multi-tenant building, things like that. Or you can do the whole property. And of course, then there's a whole scope of campuses where you're not crossing public boundaries now, but you're in a campus, whether it's a community campus or a college campus, university campus, or otherwise, or a business community, something like that. And of course, municipal and public microgrids, including all the way up to military eventually. But in this case, maybe more of the focus is on the maintenance of critical services in the public domain. And then the end markets, vary again all the way from residential to business, healthcare. Of course, you hear a lot about healthcare now, and of course, not all of the facilities we've heard of have proper backup power, but some do, some don't. And of course, the military is very active in looking at microgrid technology and, in fact, deploying microgrid technology. Probably the earliest part of which was the Navy, since their ships are not grid tied, if you will, when they're out on the seas. Again, campus stuff, public and private, academic and otherwise, and then the municipal type stuff, and at all levels in the government. So now I'd like to transition and get into discussion about the pros and cons of AC and DC coupling. And Louis, I'm hoping that your microphone or your sound is coming through a little bit better. So the first area that we want to talk about is AC coupling. And Louis, are you online? Can you talk a little bit about the AC coupling, how it all began? I don't know. I think we may have lost Louis. But he's actually schooled me very well, and I'm a bit of a technicat myself, so I'll go right into it. And Louis, if you can jump in at any time. In any case, an AC coupling, which was really centered around the early implementation of solar connections, if we go back at least 10 years or so, maybe more, simply connecting in solar panels through a PV inverter of some type that connected directly to the grid, so it's grid tied, and essentially you're putting the power on the grid, which could come back into the local premise, but also was just common with the other power that was on the grid. So whether it was a whole or a part of the local load, it really was connected to the grid and not directly connected to the local loads. Added to that, as the cost and availability of storage came along, was storage. The difference there is that the storage was both a load and a supply, although a lot of early implementations did not, again, have an ability to take that stored capability and put it back into the local loads. Again, it was grid tied and to supplement the inverter from the solar panels as well. But as time went on, a couple of different things happened in the inverter technology area to expand capability here. One was to have inverters that could take in both the PV, which needed to be managed in a different way than batteries did, but in a common converter, or inverter rather, and providing, again, the linkage back to the grid. Generally speaking, when you're AC coupled, you then have to put in a disconnect of some sort to the grid if you want to use that power locally, so that you don't feed the grid tied power in a grid failure event. In any case, the complexity of the microgrid, as even with just storage and solar, tends to tax the ability of the inverters to be commonly synchronized. And although it can be more efficient, particularly in a simple arrangement where you're just having one source like PV that you want to add in and you have some storage, it can get quite complex at the same time. And again, with the need to have some sort of electronic switching to make sure that you're not backfeeding the grid when it's when you need to be isolated. In any case, people did start to move even early in the game to inverter technology that only dealt with the final result, and the combination of DC sources like PV and battery were actually managed in a DC bus format, so that you only needed single inverter conversion for the final grid tie or to the AC tie back to loads. So this did start to simplify the electronics a little bit, where you'd have these internal DC coupled buses. In very simple systems, this didn't always make sense, although as costs started coming down on things, it starts to make more sense. But it's still, depending upon the exact application, the choice is still pretty open as to whether you should use DC or AC coupling from an economic standpoint. It's when you start to get multiple sources, more and more sources, that the AC coupling starts to show some deference to the DC coupling, in a sense that it is handicapped by the fact that each source, being that it's a different source of DC power or AC power, needs to be separately managed and synchronized and put on a bus, a common bus. And of course, that bus also needs to be isolated with some sort of switching back to the grid. So this does add more equipment and a little bit of complexity, a little bit more complexity than you would normally have with DC coupling. And Louis, are you back yet? Just checking. Okay. So if we move to the DC coupling, what this means, of course, is that everything is common to a DC bus, including sometimes the AC generated sources. So they are put onto the DC bus, so they don't need to be synchronized. But Louis, are you there? Was that Louis talking? No? Okay. Just checking. In any case, what this does is actually reduce the cost of
the telephone now is working.
Yeah, go ahead, Louis. You want to comment on how the DC coupling is a better preference sometimes when you have multiple sources?
Yeah, so I apologize about the different problems. I tried with two phones and it wasn't working well. So what I wanted to say is that there are cases where DC makes more sense. One of the problems with AC microgrids is that when there is a grid disturbance, you have to quickly disconnect the grid from the microgrid. For those cases, they use static transfer switches, which are fast switches that disconnect within a fraction of a cycle. But then the problem again is that this is a device that is producing losses and is used very little in the microgrid. The other problem that they have is that the system has to change operating modes when it goes from on-grid to off-grid, because basically what happens is that in on-grid you are following the grid, but when there is a disturbance and your system has to change to off-grid, you have to do it quickly, finding resources that will control the voltage and frequency. In the case of a DC microgrid, I think there is a big advantage in the fact that there is an inverter breaking the direct connection between the AC grid and the DC bus. And that means that any disturbance on the AC bus stops at this inverter, and you are always running some type of voltage control on the DC bus. So the transfer from on-grid to off-grid is possible to make it much smoother in the DC microgrids.
And when you're connected to the grid, you have a lot of what I guess people call frequency momentum, right? So it's a little bit easier for things to follow. But if you're disconnected from the grid and you're actually forming your own, you're generating your own frequency, I guess, then everything there, which is relatively low power, has to try to synchronize to a frequency with very little momentum, right?
Yes, basically inertia is a big part of the AC grid, and in AC microgrid, especially small ones, I think there is a big problem because inverters don't have inertia. So in some cases they model inertia in these inverters, trying to make it better, but you have to deal with reactive power, with voltage, with frequency, and of course in the DC case, as long as you keep the voltage within the right range, I think is better. One point that I wanted to make is that I don't believe there is a war between AC and DC, really. Maybe in the 1880s there was a war, but right now there are clearly cases where the AC microgrid is better. There are and there will be equipment that works in AC, but what we are trying to say here is that there are other cases where DC makes sense because maybe the microgrid is smaller, so you have more problems to control the AC voltage and also frequency. Well, maybe in these smaller microgrids, DC makes sense. I can see a future where we have a very large AC microgrid that is feeding many smaller DC microgrids that are dealing with the local resources and the local energy storage.
Yeah, so some of us talk a lot more now about DC only because it's something that wasn't talked about very much before, and almost everything was done in the AC mode. But it's not that DC is always better, it's that it is sometimes better, and therefore it needs to be sort of brought out and discussed in greater detail because it can actually make big differences in some of these systems. I know that we reviewed the material that Schneider Electric had, and they indicated in one of their, this happens to be a 20 megawatt solar storage system, where there were significant savings in the equipment when they went to the DC coupled buses. And this again was in a fairly large system. And by eliminating some of the switchgear that you talked about, and also reducing the count of transformers and things, they were actually able to save a fairly generous amount of money. Also, you mentioned that sometimes if you have things in the system that are sort of sitting there and kind of parasitically take some of the energy just because they may be needed from time to time, like a static switch or what have you, an electronic switch. They do take some energy, and if their usefulness is only very periodic, then you can actually get some more efficiency out of eliminating some of that equipment as well. There are, I guess, a few other things about using multiple inverters in a system, and some of that is a little more technical, but can you review a few of these other benefits for us, Louis, like ramp rate and things like that?
Yeah, so basically features like ramp rate and maybe clipping of the solar are possible to be solved with AC systems, but what we are saying is that is a more natural way to solve the problem with DC. The clipping, for example, comes from the fact that we oversize the DC solar with respect to the size of inverter in order to make a better use of the inverter, right? But what it means is that when the power available from the solar is above inverter rating, we have to clip it. Now, if we join the solar with energy storage using DC, we can recover this portion of the energy that is lost. Similar way, when we are ramping the system and in a DC microgrid where there is a clean and direct interface between the microgrid and the AC grid, we can ramp it in a more clear way than in the AC microgrid, where we will have to basically manage the different inverters to produce these ramp rates.
And I would imagine the charge controller on the energy storage then, it can take in the DC, and therefore you don't need to have a separate rectification of AC to go back into the charge controller.
Right, exactly.
Okay, and then there's a question, and I've always, I don't know exactly how it applies in every case, but there's a lot of discussion about edge harvest, when the sun is just barely up in the morning, or there's cloud coverage, or the sun is going down in the evening. There's a portion of the solar harvest that isn't usable if you're not careful. Is that right?
Yes, especially if you use a large central inverter early in the morning or late in the afternoon. It's difficult to extract all the energy that is coming from the solar panels because it's very, very small. Now, it is possible to make it work in AC when you use smaller inverters, maybe string inverters. But if you have a DC coupled system where you have sections of the solar panels that are handled by a DC-DC converter section, then it's much easier to get this small amount of energy that is early in the morning or late in the afternoon or when it's cloudy. Of course, if we use a very large DC-DC converter, this benefit will be lost. But one of the advantages of using DC is that you can use a modular approach in the interface between the solar and the DC bus.
So if you take all of these factors, what it really speaks to is the fact that you need to analyze the use case that you have, the scaling, the size, what sources you have either now or you intend to have. Are you going to grow the system over time? Are you going to add solar? Are you going to add storage over time? And some of those influences kind of point you in one direction more than the other. So again, this is a list that was shared by Schneider Electric that talked about the fact that all three types of coupling are in play: the DC coupled, AC coupled, and hybrid systems that have both are in play. You just need to be careful as to how to apply them based on use cases. Now, I want to kind of switch to what you're doing at Emera with this block energy system. And talk a little bit about where you're using the DC coupling that's a little bit different than most people would think.
Yeah, so basically what we have is a concept where we have AC grid interface into a DC bus. We are using battery storage to control the DC bus voltage, and then we are using this voltage to distribute the power to the homes. One of the aspects of this project is that we exchange energy between the different homes depending on the local needs. So, for example, if you have a home that is in need of high energy, and then you have another home that maybe is empty or it doesn't need too much energy, the system automatically moves energy between the homes without having to send specific commands to each one of the homes. So what we are trying to create here is a flexible plug-and-play DC microgrid for the distribution of power to groups of buildings or homes. As part of this, we have built a demonstration project that is feeding about 9 buildings in a military base. So each one of these buildings, they are small homes there, and each one of these buildings has some energy storage, and most of them have also solar on the rooftops. So what we have is a 750 volts bus that is feeding the homes, and then we have an interface between the high voltage DC bus and the homes. The homes are running basically at 380 volts. We do have inverters because most of the loads are AC, but we have the option, of course, to easily incorporate DC loads as they become available. Another feature of this microgrid concept is that we can interconnect sections. So if we have 2 microgrids that are beside each other, we could send energy from one microgrid to the other. And one more benefit that we can see with this concept is that for the AC utility, the microgrid is a single element. So we have like a local energy management that is dealing with the local solar and local battery storage. And then we have an interface with the AC grid that is dealing with those services that we are also providing to the grid, like voltage control, reactive power. So this is a concept that has been installed and has been running for about 5 months, and now we are moving into creating a product based on this demo project. Mm-hmm. So we are taking a more optimized set of parts, and we are going to develop a plug-and-play DC microgrid system.
So essentially, the individual buildings and places in the community where you can mount solar, some of them probably not all ideal, maybe some places have more solar than others, but you get to then common that in a way, or at least share it in the network. And if somebody has, as you say, less use or less load, the energy isn't clipped or lost, it's actually put out on the system. Where it can be either used or stored wherever there's available uptake for that. So this is an interesting technology in the sense that one of the complaints, I guess you'd call it, about solar, for example, is that in urban or suburban areas, you don't always have the spatial area to get significant amounts of power to power all the uses in the community. But actually, if you deploy it in this way, using house rooftops and building rooftops and so on, and putting it on a common bus, the network effect of commoning that availability, although business-wise or from a business model standpoint, it might be transacted still on an individual premise basis, gives you a lot of utility that you wouldn't otherwise have. And I would imagine because you have a DC bus, just going back to this previous slide, you could either input AC or DC into the premise, the building, right? Because you're actually on a DC bus. So that means that if somebody had vehicle charging that could take DC or something, they might want to have DC coming into the premise or into that charger at least, and eventually maybe even supplying some of the information communications equipment that's all electronic in the home or building. So it is.
Yes, actually, in this demo, we have a fast charger that is directly connected to the high voltage DC bus, but we also have level 2 chargers placed in 2 of the buildings. So what it means is that we have the option of interconnecting EV charging on the DC bus directly, but if there are no DC chargers available for a specific car or something, we can still use the AC chargers. So the nanogrid, what we call the small box that is beside the homes, has an internal battery, and it has 2 outputs. One is an AC split phase, and the other one is a DC voltage that we can use for EV charging or for any needs inside the house.
Yeah, that's really interesting. The interesting aspect there, and I suppose if you consider vehicle to grid, where people are at least contemplating using the batteries in the vehicle as backup, those batteries could somehow be coupled back into that DC bus as well without having to go through an additional inverter.
Yes, the system could move energy from the homes to the bus and from the bus to the home. So if you have a car that is connected to the home line, the energy management will make a decision of how it handles this charge that is in the car. And if we decide to use it, then we are going to move energy from the car into the bus. The other aspect of this project is that we are using very different amount of solar in the different homes, because we want to prove what you just explained, that when we have a home with a large amount of solar, it could exchange energy with a home that has less solar. So basically what we are trying to prove here is the concept of sharing energy resources between buildings.
Yeah, I know that in my neighborhood, my home faces south and a pitch of the roof faces south. So I could get pretty good exposure, solar exposure all day long, but my neighbors across the street basically are in the shadow all day long. And the back of their house is blocked by other houses. So it's interesting that it's a very unique way of sort of getting the benefits of having this sort of distributed array, but also having it common together so that you get the most out of the system. And up at the community level, it seems to me that when you get into things like fleet charging, as communities look at electric transportation, electric motor transportation in buses and subways and cars and so on. That the charging, which there would typically have to be fast charging in order to maintain the fleet availability all the time. Again, DC, so that gives you that natural coupling upstream in what you're calling this energy park up the top of your block energy. So any last comments on that, Louis, before we open it up for questions?
Yeah, so basically what you said is right. The system is flexible in the sense that we can use solar in the central park. We could have energy storage in the central park. We could have EV charging in the central park, and we could also have resources at the homes. So we are trying to create here a platform where we can build different types of microgrids depending on the specific site, specific customer.
I guess, you know, one last point I wanted to make. I suspect that many people on the line today are technically very aware of the benefits and challenges with both AC and DC. But a lot of people still have that old thought sort of paradigm that they didn't think that DC could travel very far over wire for some reason, principally because of resistance in the wire. But actually that had to do with voltage and not frequency, right? So in your system, I assume that you're using higher voltages in parts of the system, and as you get closer to the loads, lower voltages, so that your voltages are high enough that you're not suffering wire loss. You may actually even have an advantage over some single phase or three phase AC, right?
Yes, initially we see the system as a system that will serve relatively small groups of homes that are close to each other. So we are assuming that between the central unit and the homes, the maximum distance is about 1 mile. We are using at the moment 750 volts just because it's a voltage where we can find the different components we need. But as we get progress in DC-DC converters and potentially we have more and more equipment running in the 1500 volts, we will be able to go to higher voltages. Again, I see this as a potential system where we have an AC microgrid, which is large in the order of multi-megawatts, and then is feeding 10, 20 DC microgrids that are responsible for running the local loads. At the moment, in the demo, we have two voltages, the 750, as I mentioned on the bus, and the 380 volts in the homes. But of course, the flexibility of the system is that as we have different types of loads and different needs, we could create different voltages.
Well, that's great. Let's open it up for questions and see, Greg, if you have anybody so far that has questions on some of the topics we've covered.
Yeah. So one, which I think you covered, just some of the voltage discussion, but there's just a general question for Louis about where you work, a little bit about what you do from a background in terms of this, and then like what region. So what region specific examples do you have of the coupling that you can present?
So I live in Canada. I live about 45 minutes west of Toronto. Emera is a company that is based in Halifax, but Emera has a company in Tampa, which is the one that is working on this DC microgrid. So I'm working from Toronto for a company based in Tampa, Florida. And the demonstration project is in New Mexico, actually in Albuquerque, in the Kirtland Air Force Base.
Right. I've had the opportunity to visit Kirtland Air Force Base, and I know that based on the success down there, that the base commander is very interested and excited about expanding it because the stationary base resources are more and more being considered to be critical, as for example, we've seen in this pandemic, whether it's the military or the National Guard, Homeland Security, et cetera, et cetera. And that'll actually be the topic of our next webinar, is how microgrids are being used in those critical sort of support, infrastructure of the Homeland Security and National Guard, et cetera. When I was at Kirtland, but it was interesting to see that you could see that it had both military application and inference, but also it was applied to residential buildings there. So and covered even the what looked like a small commissary and an RV park where people would pull in with their RVs. I guess the transient military. But in any case, it seemed to fit the bill to satisfy a lot of those different applications, and yet it was a very simple and fairly straightforward system. So
yeah, so the basic business plan that we have is that this is going to be in front of the meter system. In other words, we are going to sell this system to utility companies that are going to own the energy storage and the solar. This way we avoid asking the customers to put money in front, and the utility will sell the electricity to the customers. If the cost of the batteries keeps going down the way we expected, and if the cost of DC-DC converters also come down, we think that we are going to have a cost of electricity that is very close to the cost of electricity we pay at the moment in many states of the south of US.
And that's another aspect of all of this type of topology, is you want to have as many choices as possible. Some people have often contemplated that the use of microgrids, particularly at the premise level, are threatening utility interests, and vice versa, that the utility needs to own everything. I think what's represented here is a lot of options, whereas utilities can participate as well as individuals, depending upon either by contract like we do with cell phones and everything else, or by ownership. In any case, you have another question, Greg?
I do. This one comes from Stephen Willens. It's, when is DC coupling advantageous for a single site microgrid with multiple sources and loads? So an example mentioned there could be a single site industrial or education campuses, healthcare campuses.
Yes, so I think it all depends on what is the main energy source, right? If you have a microgrid where only 10-15% of the energy comes from solar, maybe it doesn't make sense to have it DC. Now, if we have a case where you want to have 50, 60, 70% of the energy coming from solar, if you have a CNI building, for example, where most of your load is lighting and maybe variable frequency drives, those are the cases where I think this makes sense, because it's already there. It's already part of the system. We're going to remove the front end that goes from AC to DC, and then we are going to run the system on DC. So it all depends on the size of the system and where the energy is coming from.
Yeah, and I think the willingness to integrate the DC further and further into the infrastructure of the building or what have you. I know I've seen now variable speed HVAC, big air handlers and things like that running on DC with DC motors, or DC drives, at least with a DC section into an AC motor. So if you can utilize DC, and your some of these buildings absolutely have the objective of being net zero, and sometimes net zero is misinterpreted as it has to all be real-time net zero, but it's either the majority of the year, depending upon what's using your energy. Some of the buildings are actually, I know the American Geophysical Union building in Washington, D.C. recently completed a DC coupled microgrid. Actually, and most of the uses internal to the building now are DC, and it actually is a net zero plus, what they call a net zero plus. So it's actually exporting electricity the vast majority of the time. So they have a lot of sources though. They have a lot of solar on the roof. It is a flat roof with a lot of solar, but it also has some other generating techniques which are very novel. It has a biodigester in it. It has, they're doing micro hydro on some of the water drains and things like that. So there's a lot of interesting sources that just made it absolutely easier to do it with DC than couple it with DC. Now, there are still some AC uses, so they're using inverters, but they're inverters that don't have to synchronize with the grid. So, right, you know,
Right.
I always jokingly say my hair dryer doesn't have to run synchronous with your hair dryer, just in a different building. I can use my own phasing frequency of AC, and you can have yours over there with separate inverters. They don't have to synchronize. So when you try to synchronize everything, you know, think of it in the United States, we because of the fixed frequency of the grid, we're actually trying to synchronize millions of devices that run that have an AC frequency input or an AC frequency use to the same phasing, and that's very difficult to do, and can be expensive depending upon how close you want to maintain your frequencies. Another question, Greg?
Yeah, so this one refers back to the block energy concept. There are two questions in general that we have that I think relate to each other. So one is, with the block energy concept, how would you manage the pricing between the block segments? And then a follow-up question to that is just more in general, how do the microgrids couple on the AC grid, and who pays for the electricity?
Okay. So again, the concept here is a front of the meter. So what happens here is that the utility owns the central part of the microgrid, and in most cases, they own the home batteries and the home solar. So who pays for the electricity? Well, the utility will install the project, and they will sell electricity to the homes. The interconnection with the AC grid is through a simple inverter, and of course, if the utility owns both sides of the system, the AC grid and the DC microgrid, they will be able to adjust the price according to the cost of equipment and the use of electricity in the homes.
Yeah, typically your block energy connection is going to be at a substation or even after the substation, so you're not on the transmission grid. And again, you're selling AC and or DC maybe in the future to the end consumer. So everything in between, they don't have to have a regulated pricing or transactional pricing. They may look at it in terms of transactional cost. So the same kind of consideration goes into, you know, should I charge the battery, or should I use the battery, or should I generate power, take some more power from the grid? All those considerations are there. If they're utility owned, they're going to be more made on a cost basis, and a utilization, maybe service requirements.
Right.
If you're the consumer at the end and you own the asset, you're going to make it based on more of a transactional price basis. So, you know, the system, the way it's contemplated now, is sort of in between a substation and a premise, and it's all on the outside of the meter, so that the utility will set pricing, you know, to the end consumer in that case. I did want to mention that eMerge is working with a fairly large group of companies and people on a DC metering, revenue grade DC metering standard. For those of you familiar with the ANSI C12 regulation or standard for AC metering, we're currently working on a DC version of that same standard to provide for the opportunity for people to sell DC in the same way that they sell AC. So there's lots of different business models that can evolve from that whole concept. You know, there's ones that maybe a municipality or a utility will use for incentivization of the use of DC if they have DC, or there may be direct metering if it's in a transactional, you know, peer-to-peer or, you know, retail sale of DC. Next
And
question. Yeah, go ahead, Louis. You wanted to?
the market that we are trying to catch initially is the market of new home builds, because in that case, we could build the homes already with the DC system integrated. But that doesn't mean it's the only market, because there are some other cases that are called maybe the last mile, where the end of the distribution line has a lot of problems with faults. And in that case, we are finding that it makes sense also to change those last pieces of the mile into DC systems.
Yeah. Okay. Another question, Greg?
Yes, I think we have time for one, maybe two more here. One question that we would be interested in hearing more about is the safety issue. So could you go over the differences in common safety mechanisms required by utilities for islanding, so such as switches between DC and AC coupled microgrids?
Okay, so yes, the safety is part of the new things that are in DC systems. The islanding detection of a DC microgrid, in my opinion, is simpler than for an AC microgrid. At the end of the day, you are connecting to the grid through an AC inverter. But of course, you have to think about many other aspects, like the response is in case of a short circuit. Maybe the grounding scheme that we want to use in DC microgrids is slightly different than what we have at the moment. So the other aspect is that, as you know, the DIDT in DC systems is much faster than it is in AC systems, where there is an inductive component on the impedance. So the development of protection methods and protection devices for DC systems is something that is starting now, and that is very critical to the extensive use of these systems.
Okay, I hate to say that we have run out of time, and I wanted to get in just a few last comments if I could, Greg. But the people who have submitted questions, we're going to try to record those questions, and we're going to have a site eventually to post questions and answers. But I wanted to point out that if you want really a full story of this whole subject, one of the great opportunities is to attend the North American Smart Energy Week that will be in Anaheim in September, where we have our fingers crossed that everything will go well there. But that particular event covers everything from solar, wind, storage, microgrids, EV infrastructure, fuel cells, et cetera, all the way down the line. And you can, registration for that is open if you go on the web under solarpowerinternational.com, and you can do that. We also have a series of additional webinars that are coming up. As I mentioned, the one on the 19th, just a week from today, will be on Homeland Security, National Guard, domestic military base, and so on. And you can see the list if you go to the website, the Solar Power International website, and go to events. And maybe Greg, you can mention the website that's available there. But you can sign up for any of these webinars. They're all free. They're all going to cover a variety of subjects, and we'll have a variety of experts at each of the webinars to answer your questions. I also wanted to say another thank you to our sponsors, Emera, who is going to be in booth 2904 at the show. Again, makers of inverters and a lot of other equipment that goes along with that. We also have Power Engineers, an engineering company who supported this series. They'll be in booth 2908. NorCal Controls, also at SPI, they'll be at booth 2020. And they are providing automated control solutions for a variety of applications, DAS and SCADA and so on. And last but not least, the company that Louis is from, Emera Technologies, makers of Block Energy, with this new plug-and-play platform that they're going to roll out this year. And they're sponsoring the Microgrid Theater at the North American Smart Energy SPI this year. So we thank them for that. I also want to mention that tonight we're going to pilot a series on evening. It's called Energy After Hours. It's at 6:30 tonight on the web. We'll be streaming that as well as doing a webinar. Again, if you want to, you can sign up at the Solar Power International site on the web, and hopefully you'll join us there. We're going to be talking more about the fragility of our existing grid and how fast we can actually build resilience into the grid and what's taking so long, so to speak. So that'll be the discussion for tonight. So thank you very much, and I hope that everybody had got something out of today's webinar. Greg, do you have a final word, or are we good to go?
I think we're good. I mentioned in the chat there, we do have Energy After Hours today. So just head to the events.solar Think Engage Connect page, and you can see all the future webinars and sign up for them there. Otherwise, we'll be in touch with an email of a video recording of the session. And thanks, Brian and Louis, for helping us out today.
Thanks, everybody. Bye-bye.
Okay, thank you very much, guys.